Alright, so here we are with dot products of vectors. So the idea of a dot product is actually going to be used within a formula. So it doesn't necessarily tell you anything in a result, but it is going to be used in telling you something later. So anyway, it's just kind of like an operation. So here we are with our definition of dot product, or what they call inner product. Literally never heard it called that. Okay, so depending on, I suppose, who your teacher would be. So we're looking at vector u here, and u is given as u1 comma u2, so those are its component pieces, and then we've got vector v, and its components are v1 and v2. So in order to get the dot product, again, very much looks like you'd be multiplying, but it is not multiplying, so watch out for that. It's not actual multiplying, it has multiplication in it. Okay, so there's a difference there. So when you see this of two vectors, do not just multiply immediately. You do multiply the x pieces, if you will, the horizontal pieces of your vector, and then the multiplication of your vertical pieces, and then you add the results of those. So again, product of horizontal components plus the product of the vertical components. And again, that is not the same as just multiplying everything out. So it does result in a single real number, so like 5, okay, which is very interesting. So anyway, and again, used in a formula later to find angles, so not necessarily telling you anything about like the speed of something. All right, and then an orthogonal vector is where vectors u and v, they could be orthogonal if their dot product makes 0. Meaning the product of their horizontal components would be the opposite of the product of their vertical components. So anyway, just interesting to think about. So you could get a 0 and you'd have an orthogonal vector. So taking a look at our next slide, we've got some examples. So we're going to find the dot product and state whether the vectors are orthogonal or not. So in order to do that, we're going to take our horizontal piece and multiply by your other horizontal piece, and then add that to the vertical pieces being multiplied. So we've got negative 12, and to that we're going to add 14, and so our resultant value is going to be 2. And so of course 2 is not 0, and so it's not orthogonal. Oh, that's a no. Alright, then we could do our next one, and of course looking at this non-traditional formatting, that's okay. We're still looking at this being 3, negative 4 in component form, and 10, 9. Either way, we're going to go ahead and multiply the horizontal pieces, so 3 and 10, and add that to the vertical pieces, which are negative 4 and 9 being multiplied. From there we get 30 that we're going to add to negative 36, which of course is the same as subtracting, and so that one also is not orthogonal because it does not equal 0. Okay, so when do we get to use it? To find the angle between two vectors. We do have that other piece that can also find the angle between two vectors. Well, no, actually that's just the standard vector. So this one's just between two vectors versus between the vector and the horizon. So in order to find the angle between two vectors, go ahead and use your dot product. So notice we've got dot product on the top, and then from there we use the magnitude of both of the vectors, and those are being multiplied. Notice it's not necessarily in there, but because they're right next to each other, you would potentially multiply those, not dot product them, because they're values, so you wouldn't actually get a number. And then, of course, you're going to take the cosine inverse in order to get the answer, but to kind of make it look nicer, they say that cosine of that angle. But we will most likely be using this idea a little bit more because that's how you would solve it anyway. So, angle between two vectors. Cool. So we're going to go ahead and find the angle between these two vectors. So that means that I need to find the magnitude of vector u, so I'm going to take 4, square it, add it to 7 squared, and square root. So we've got 16 plus 49 that I'll be square rooting. And so that results in the square root of 65. I'm not necessarily going to get the decimal equivalent of that because it's not really going to simplify much. Then we've got the magnitude of v, which means we'll take -3, the quantity, square it, add it to 2 and square. And so we're getting the square root of 13. So in order to find that angle, we also need the dot product, so I will do u dot product v. And so in order to get that, we're going to take the components of the vertical pieces. So we've got 4 times -3, and then we're going to add that to the horizontal pieces, other way around, these were the horizontal, and then the vertical are 7 and 2. So we end up with -12 plus 14. So we're at 2 for the dot product. So that means that in order to put this all in there, in order to get the angle, we're going to end up with 2 on top, because the dot product was on top in the formula. Again, we're using this formula here, dot product, and then the 2 magnitudes multiplied. So we'll have square root of 65, and then square root of 13. So let's see. Oh, sorry, I wrote this backwards. We need the cosine inverse of this, and that will equal the angle. Because of course I went through and got 0.0688 and was like, what's happening? It's because I need to take the cosine inverse of it. So 0.0688 is going to be our angle. And so we end up with 46.53 degrees. So that means if I had both of these vectors, the angle between them is right here at 46.53. Alright, so then we do the next one, the same process. Again, the more you do it, the more you remember what it is that you actually need to do each time. And, oh, I did that wrong. Oh wait, no I didn't. I'm thinking of the dot product. Okay, so, and 3 and 1 is 9 and 10, so square root of 10. Woohoo! So absolute value of v makes the square of 3 and the square of 9. So square root of 90. Our dot product, I have an issue with being able to actually write u's and v's differently. Okay, I know I can put that little tail on it, but I just don't. Okay. So we're going to take 3 and multiply it by -3, and then add that to 1 times 9. So -9 plus 9. And so we have a 0. So what does that mean? Well, the dot product is 0, and so you literally have a 0 on top over the two pieces being multiplied. So square root of 10 times square root of 90. So it doesn't really matter what's on top. Because 0 out of what's of anything is going to be 0. So I need to take the cosine inverse of 0. And so that means that we are at 90 degrees, because you don't go over any when you think of horizontal movement and cosine on the unit circle to get up to 90. Potentially that means it could also be 270, but yeah. Alright. So, we've got a bunch of things going on here for work. And actually, as weird as it all is, I mean, you can talk about force and all that stuff, but basically what it comes down to is a formula for work is going to be work equals distance. So if you know what distance the thing is traveling, multiply that by the cosine of the angle where the work happens. And then if there happens to be any weight, you would multiply that in as well. So what happens is sometimes they don't mention a few of these, like it doesn't move any distance. There can still be work involved if something isn't moving any distance because, for instance, I'm imagining holding like some sort of weight. It's not moving, but of course I'm putting forth effort or work to make it not move against gravity. So in that case, we're going to go ahead and work through using this idea. So, we've got a little idea here. Apparently, Harold is sitting in a sled on the side of a hill at an incline of 30 degrees. And the combined weight of Harold and the sled is 150 pounds. And Hazel is holding a rope, keeping Harold at the top of the hill. And so again, Harold would be going down the hill if Hazel wasn't there holding on to that. So what force is required for Hazel to keep Harold from sliding down the hill? Here we go. Let's draw a diagram. So here's our hill that Harold's going to go sledding down. Maybe. Yep, on a sled. The hill itself is at a 30-degree incline, right? That's what they said here. And so up where Harold actually is going to be 60 degrees because I'm making a right triangle. So let's say the hill continues. We've got Hazel up here kind of holding on to the rope where Harold is sitting so that he can go sledding. Yay, sledding. All right, and then there's this rope at the end of the sled. Okay, lots of good stuff. So, the distance is 0. Because, again, keeping Harold at the top of the hill. So that's what's happening here. The weight is going to be 150. And then the angle at where the action is happening is actually going to be 60 degrees, right? Because it's not 30, that's at the bottom. They're at the top right now. So that would make a difference. All right, so in order to get the work that, or the force that's required for Hazel to keep Harold from sliding down the hill, we would need to determine that by taking the weight, which would be 150, and multiplying by, as the formula said, cosine of 60. So 150 times cosine of 60 means that our work, or the force that we're using to keep Harold from going down the hill, or at least Hazel is using, is times cosine, make sure you're in degree mode, 75. And it is foot-pounds because that's the idea of work. It's given in foot-pounds, unless, of course, sometimes there's like tons or something going on. Because the distance, as we're looking at it, would have been in feet, that anyone would travel in this, and then pounds. So that's your work, or your force. So we're going to find the work done by pushing a 40-pound box from point 00 to 40, meaning that it is going across. So of course there's friction and all that good stuff involved. But right now, to find our work, or our force, that's needed to do this, we're going to take the weight, multiply it by cosine of the angle of where the work is happening, and then the distance. So if we do that, the weight is 40 pounds. The interesting part about the angle of where this is happening is that it's 0. Cosine of 0 is actually 1, so it's not really going to change much of the outcome. And then we've got our distance, which would be 4 units. So might be 4 feet, whatever it is, it's going on a chart from 00 to 40. And so we need 40 times 1 times 4, so 160, and again, foot-pounds. All right. Next one, we're taking this 40-pound box that we had before. And if you didn't know, pounds is, I hope you do, but either way, pounds is given as a L and then a B as its abbreviation. We'll just go with it. Okay. Now I need to look up why. Okay, in case you're wondering, of course, it happens to be, some sort of where the word came from, but apparently the word pound comes from the ancient Roman, where the unit of measure was libra pondo. So, libra. Is actually what pound is, and so libra was abbreviated LB. So, anyway, good to know. Yay, internet. Okay. So, we're going to find the work or the force needed for this. And so we're going to need our weight, which is still 40 pounds, multiplied by the cosine of the angle where this work is happening, and then the distance. In order to get some of those pieces, we are going to need to draw a diagram of what's happening. So you push the box 4 feet up an incline plane in the direction of 8, 2. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 2. Alright, so that's going to give us an angle that we're talking about. And again, we are down here pushing up, so we just need this angle over here. We know it went up 2 and it went over 8, and so we should be able to find that angle using trig. And what else do we need? Oh, this incline is 4 feet, so we don't necessarily need to calculate that. So we do know distance is 4. So in order to get that missing angle down here, we have the opposite to that angle, and we have the adjacent to that angle, so we're going to need some tangent. And so in order to solve, we'll take the tangent inverse of both sides. Again, in degree mode. Whoops. 2/8, which is 1/4. So we're going to get an angle of 14.0362 degrees. Okay. So we've got 40 times cosine of that angle, and then times 4. So it's going to take 155.22 foot-pounds in order to move that 40-pound box 4 feet up that incline at 14 degrees. Anyway, very exciting moments. So, on that note, you do, have an assignment, but of course that will be given in the next video, so you can get to work on that. Remember that we do have our formula sheet, so as we're looking through what we used today, we definitely have dot product, angle between two vectors calculation, and then also this work idea in order to find the force needed. So there it is, 6-2.